Good morning, everyone. So today I will talk about a quick short introduction about Bramble CFD, and then I will go through a summary of the different noise factors that we conducted studies, go through more deep dive between the methodology and the results observed in each one of them, and wrap up with a conclusion. So first, just a quick introduction. Bramble is part of the most well-known AutoCFD group, which was a CFD consultancy company, and we are basically a CFD cloud platform built on top of OpenFOAM, with a focus in speeding up and automatization of the CFD process, from the pre-processing to the post-processing. We decided to conduct three main studies regarding noise factors. The first one was what would be the impact of having different initialization strategies for transient runs. One other aspect was as well if we have a different file structure or modularity in the input geometry. So if you have like one single part representing your vehicle or multiple different CAD parts as an input, what would be the impact in terms of noise factors? And also there was an embedded study between the initialization and the input geometry, which was what was the impact of running the solution for longer, because it was quite observed that running the solution longer, it helps with reducing the noise factor, but you're increasing the costs. So the objective was trying to account for what is the impact of running longer, basically. And all of these studies, they were conducted on the DrivAer geometry at the case 2A, without the wheel deflectors. So first, talking about the initialization, we decided to have different settings to try, which was changing the time step in the initial washout period of the, in our case, our transient solution. And for this particular study, we decided to perform in the committee mesh, in the ANSA mesh. And all of these studies, they were performed in our in-house OpenFOAM V1806 code, with a fixed, let's say, final time step of 5⁻⁴ seconds. And all the runs, they different simulations, they were run in total for 5 seconds. So what was changed was the time step size in the for initialization in the beginning, and how long this was used to speed up the convergence, basically. In terms of drag overall results, there was quite a spread between the different initializations, and which had a convergence with increased time, averaging time. So this graph now, it's showing the relative delta between the for each of initialization technique for the total of 5 seconds, which was 3 seconds of averaging time, compared with 1, 1.5, and 2 and 0.5 seconds of averaging. And as expected, it was possible to see that there's a trend that running longer, you decrease this delta the direct delta difference, and going from around 0.8 counts maximum to from 2 seconds onwards, it goes above 0.4, which is could be considered kind of an acceptable range. And this was the comparison between the baseline. That the baseline was was our best practice that we use, which is a constant time step from the initial of the solution. So actually, we always initialize the solution first with 500 iterations of runs, and then we start up the solve. But in terms of drag differences, it was quite high for 1 second of averaging, almost reaching 2 counts. But as showed before, with increasing time, this kind of uniformly converges. But it's still kind of almost one count, between 0.8 and one count, which for error development could be significantly. Going a bit more in deep dive where the drag difference main comes from, one of the two regions was this region around the rear of the front tires and at the rear deck, which it was some results that were quite in symphony with what we observed yesterday with the different codes. These are, let's say, quite sensitive region due to transient effects. And this is like some of the probe results in the rear deck, which there's kind of a bit of difference in the base pressure between the different run variations. And looking a bit of in the flow topology, mainly the one at the top, it was the run called run 1. The recirculation region above the rear deck kind of has a different structure, a bit compared with the others, which might indicate where these differences are coming from between the simulations, even though it's all of them were like validated by MinCalc, had like 3 seconds averaging, but we still have this kind of differences even with kind of robust methodology. This is also an interesting plot. It's about the delta surfaces in the of the pressure between the baseline and the other variants. And there's a, as expected and showed a bit yesterday, this was kind of correlated with this quantity, which is the CP prime to mean, which is the difference between the average and the instantaneous pressure values. So basically where you have high fluctuations, which is kind of a bit of expected as well. Now talking about, I will actually to speed up a bit. Talking about the second study, which was the input geometry. The idea was we have different customers, OEMs or different that some would prefer to upload a single part as input geometry for the CFD setup, or you can have like a really modularized with like 200, 300 parts. So the idea was, what was the impact between these different input geometries, which technically they should be the same. For this study, the only difference is because we would change the input geometry, we used our OpenFlow match, which is the Snappy X match, which had around 98 million cells. About the results, it was the drag results. One of the main differences compared with the initialization was by running the solution longer, there was not kind of a convergence between the drag values. They were more kind of shifted, which was quite different than what we would expect as well. And doing the same analysis of having the drag from the 3 seconds averaging compared with the different averaging times. This was similar to the initialization, which proves the point that like running longer, you increase your statistical range, so you're going to have better quality in terms of variability. But above 1 second, from 1.5 average time, there was not much difference, having less than 0.3 counts difference above 2 seconds, which is an important point, which is try to have like what would be the, let's say, ideal or best practice for averaging time. You can have a difference between different codes and different models, so kind of tabulating this would be really helpful. In terms of the difference, the main aspect was that running on this study, it didn't change the delta difference. This was kept, which could be explained due to, actually, I'll go back to that in a moment, but would be to the small mesh differences that could have carried on the solution, even though it's just like a couple less than 1,000 cells for 97 millions, which is not much, but there was kind of an impact. And the main impact was in this region on the wheels and in the front wheel arches and wheel house, which having a look on the flow field, the main difference was in the inflow inward of the behind the tires, which changed the separation point and basically the total energy flow from this region, which basically correlates with this difference encountered between the two cases. Just wrapping up, it was possible to kind of tabulate what was the impact of different types of settings that can have an impact on noise factors. In terms of the, say, physical time, it was around 0.8 counts for 1 second. By running longer, it will decrease this. The initialization had an impact of 1.7, but by running on, this was decreased to 0.8. And this correlation between the transient variability of the flow field and the differences was explained, was captured. And the input geometry, there was like 1.2 counts for 1 second. But the main thing that was different from the initialization, it was this difference between the effect of running on between the two cases. And for the future, one interesting thing would be the comparison, rerunning this case with the factor to see how the direct prediction when doing design changes affect that. That would be an interesting point. And that's it. Any questions?